Hey guys, this is Jeff with Reference Analog. I've got some pretty exciting guests today. I've got Imran Mangelson from dCS. He is the director of North America. And then Andrew Selka from dCS, and he's the program manager. So we're going to do a little round table, and hopefully we all get to learn a little bit. And it's pretty exciting having them in the house. So thank you guys for coming.
It's
Thanks for
our
having us.
pleasure. Absolutely.
All right, so for those in audio, I think everyone knows the name dCS. For those of us who are those of my customers who are just getting to know the brand, what do you think is the like foundation of dCS and the start of kind of what established the brand?
Oh wow. Maybe I'll start off, and Andrew, you can add to this. DCS is we're a small brand out of Cambridge, UK, and our history goes back to the late 1980s, which was really kind of the burgeoning era of digital audio, and the company evolved from the roots in signal conversion, actually, far removed from music playback, but actually for projects that were catering to Ministry of Defense projects for radar technology and so forth. And the innovations that were born out of that, and the individuals that were involved in developing that were passionate audiophiles. And they were able to take many of those innovations, and they were repurposed, if you will, into digital playback. And since that time, we've blazed a lot of trails, but the history and roots of our company, harken back to the UK in 1987, and then from there, through a kind of a long and winding road, we found ourselves into digital music playback today. But
Okay.
yeah, Andrew, would you
Yeah,
add to that?
sure. I think the one of the first projects that was one of the probably the defining project for dCS was a project called Blue Vixen, which was a radar system for the Sea Harrier, the vertical takeoff and landing jump jet. And the project was to develop a new analog to digital converter for this radar system. And in a defense use case, basically the limiting factor in the radar system was the resolution of the conversion. Basically, if you had better resolution in your conversion, you could see further. And in real terms, that means that if I can see the bad guy before he can see me, that's a huge advantage. So improving the resolution was really, really compelling. And there was a lot of research was put into how we could improve the accuracy of that conversion process to give the radar more range. And so when we later parlayed that over into the audio world, we were able to benefit from the improved accuracy of that conversion that was a result of a fairly substantial defense research project.
See, and people don't think audio is life and death. There you go. What do you guys think that is the most important thing that dCS is doing to achieve the ultimate sound quality that we're all after?
Oh, that's a great question. I think that, maybe I might tell a little anecdotal story to bring out my point here. There are a lot of companies out there that have kind of a thing, their secret sauce, if you will, the aspect perhaps of their design that they obsess over. Whether that be power supplies, or whether that be chassis design, or whether that be time domain differences, or whatever it may be. And what was really interesting is I was at out in the UK, and with a number of retailers that were there for some training. And this kind of similar question was posed to one of our lead engineers of kind of what's kind of the thing, the sacred cow, if you will, at dCS. And I thought it was really fascinating that this engineer noted, he thought about it for a moment, and then he said, by not obsessing over one particular thing. So in other words, the answer was that we take a holistic approach, and at no point do we ever have any particular sacred cow in the whole design architecture. But by paying attention to all of the little individual details, one more over or more important than another, we're able to execute a design that is far more that is far more enduring and has better accuracy, and is designed holistically. But I think that's, maybe it's not the answer that folks look for, that is kind of like, what's that one thing? But
It's the sum of the whole.
It's the sum of the whole, exactly. And so, by not allowing ourselves to be myopic on any one particular thing, we're able to achieve a design that is that is much more high performance, enduring. I don't know, Andrew, what would you maybe add to that?
So all I would add is maybe a couple of examples. I remember getting a question when we launched the Veres, our flagship product, new flagship we launched about a year ago. There's a UI module, which the front panel of which is one large screen. And I got a question from a customer, what technology did you use in the screen? And I didn't know the answer. I had to go back to engineering. Nobody had asked that before. And they said, the answer came back, it's a TFT screen. And the customer said, why didn't you use OLED? Because I thought that was the latest and greatest. Is this some cost-cutting thing? So I went back to engineering and asked, why did you use TFT? And the answer that came back surprised me. It was, well, it sounds better. And I was like, come again? And they explained that every display technology has a circuit that drives the display. And part of that circuit is a clock that refreshes the display on a certain frequency. And with this particular TFT technology, we were able to basically bypass the clock in the display circuit and use the audio clock to drive the display refresh, which means that we didn't have a dissonant clock frequency in the chassis, which was causing interference. And so when we executed the product in that way, it actually sounded better. So even the screen affects the sound quality of the resulting product. And it's that level of kind of obsessive attention to detail in every aspect of the circuit realization and the construction of the final product which contributes. It's kind of like everything matters.
Yeah. So that sounds a lot like pioneering and a new front of a way of thinking of things. And that kind of leads to my next question here. Can you, Andrew, can you tell me some of the pioneered innovations that dCS has been a part of? Because I know they've established a lot of things in the industry on how we do things. So,
yeah, I think the fundamental innovation, which has been the platform for almost everything that dCS has done over the year, was the Ring DAC. And the Ring DAC is actually an evolution of another DAC architecture, the ladder DAC. And basically, this is a risk getting way technical, but essentially, a ladder DAC uses resistors to generate current, and then that resulting current is summed to create the output signal. And so depending on how many resistors you turn on, that affects the amount of voltage that you get out at the end. And you have basically one in a ladder DAC architecture, you have one resistor for every for every bit of your digital signal. The problem, the limitation of a ladder DAC architecture is that when you realize that circuit in the real world, you want all of the resistors to have exactly the same value. But every resistor has a manufacturing tolerance, which means that depending on how many kind of decimal places you go down to, you will eventually find differences between these resistors. And the issue is that because you always use the ladder from the bottom up, so if I have a signal value of 1, I always use the first resistor. If I have a signal value of 2, I always use the first 2, etc. So I always use the resistors in the same order. That means for every one of my thousands of possible different output voltages, the error will always be the same for that given level. A 42 will always have exactly the same amount of error built into it because I'm using exactly the first 42 resistors.
And this is on a traditional ladder
This is a
DAC.
ladder. This is in a
Traditional,
ladder DAC, but that basically means that this manifests itself as harmonic distortion, which is one of the things you don't want when you're realizing a digital architecture. And so the fundamental innovation that kind of DCS is platformed on is Mike Story, the founder of DCS. He found a really ingenious way of circumventing this problem by basically using a different random subset of resistors for every single sample. So he has this little brain inside the product, which for every single sample that's converted is selecting a different set of resistors to make up the voltage that's required. And so that correlated error that's coded into a ladder DAC, and correlated error is distortion, he turns that into an uncorrelated error, which is noise. And noise is psychoacoustically very much more benign. Our brains can filter it out in a way that they can't filter it out with distortion. So the analogy I use to explain this is that, this is a very quiet room, but imagine you had an aircon system that was on, that was sort of humming, or there was like a swooshing sound in the background. All of our ears would have filtered that out by now. We'd have adjusted to that, and we'd be listening to each other. We're the signal, and that's just noise, and we're filtering it out. Whereas if I pinch my nose, I change the harmonic envelope of my voice. That's distortion because it's correlated to what I'm saying, and you can't possibly filter that out. You can't possibly ignore that. So that's kind of psychoacoustically the difference between distortion and noise. One's very objectionable to our ears, and one we filter out almost effortlessly. And the key thing that Mike Story realized is, in the digital realm, you could actually trade one off against the other. So he could take objectionable distortion and turn it into benign noise. And that's kind of the fundamental innovation on which the company is founded.
When you think about it, right, I mean, engineering, great engineering is about assessing, the various compromises and compromised outcomes that one might have, and choosing, which are more acceptable compromises to make, right? You can't steal from Peter and not pay Paul, and so on and so forth. It's always there's in that decision process what compromises one will make, and ultimately what those engineers and what Mike's Story found was that if looking at conversion architecture, which is the worse or evil? Distortion, as a result of the conversion errors, right, which is correlated to the signal path, which gets manifest into the system, or noise. You don't want necessarily either, right? But which one would be the worse or evil? And ultimately, it was determined that noise is something that is a lot easier for us to be able to deal with, and we have some really clever things that we can do in technology to be able to handle and deal with the noise. That was a much more acceptable compromise, as opposed to we obsess over linearity. We really want to make sure that the whole design leads to something that is excellent in accuracy in the conversion itself.
Okay, so why is the randomness integral to the linearity of the processing?
Yeah, by randomizing the which switches and ladders, which current devices get utilized during any particular conversion, we're able to do a couple different things. One is that within each one of those current devices, those resistors, right, they have these tolerances, and despite very best efforts to get the very best and most stringent standard tolerance resistors, there's still going to be some degree of slight error, right? But by seemingly randomizing, though, which current devices get utilized, and then being able to we're able to average out what essentially those errors may be, and we can decorrelate those errors from the signal path, push that up into noise, and then we can handle that noise through a lot more gentle filtering. But and one thing I should point out is that it appears random, but I can assure you that the mathematics that are involved, the algorithms that have been selected and honed over decades to determine which current devices get utilized and which ones are switched on and for how long and so forth, that which is a fundamental of what we refer to as the mapper inside of every digital to analog converter in the ring DAC, those algorithms have been improved and evolved over time, but essentially by averaging out those errors, the current devices were able to have a much higher, a much more accurate result in the signal.
Awesome. Andrew, how would you say that the ring DAC evolved with Apex? When you guys launched the Apex line, was it just a completely remake of the DAC, or was it like an evolution of the DAC process?
Yeah, so it was very evolutional, and it touched a couple of areas, a couple of which are related to the DAC itself, the converter itself. And a couple of which are related to the analog output stage that drives the the amplification component down the chain. So one of the things that we did in the Apex upgrade with the DAC itself was this mapper that Emran referred to. That's the sort of the brain that is deciding which subset of the resistors are going to be turned on for a given sample value. We introduced some algorithms that doubled the frequency that the mapper ran at, so it was making twice as many decisions as it was in the previous version of the architecture. We also the signal starts life at the power supply, so the power supply feeds each of the resistors in the ring, and depending on whether if the resistor is turned on, then that drives current through the resistor, which goes to the summing stage. But the power supply is like the reservoir that's feeding the whole process. And so the quality of the power supply, the linearity of the power supply, is absolutely essential to the quality of the result. And by lowering the impedance of the power supply, we were able to reduce the amount that the power supply was affected by the changing load that was being placed on it. The more latches that switch on, the more draw there is on the power supply. If the impedance of the power supply isn't low enough, then the current will sag. Rather like if you turn all the lights on in the house and the ones that are already on start dimming, or you turn the oven on and the lights dim a little bit. There's a similar effect with the power supply in a DAC. And so we made the power supply stiffer. Similarly, the clock, the master clock, which is timing the actual conversion process, that is connected to each of the latches because the clock is defining exactly when the latches turn on and off. And similarly, the more latches that turn on, the more draw there is on the clock supply. By lowering the impedance of the clock line, we were able to make that stiffer and more resistant to the fluctuating load that was being placed on that. So there were some improvements in the circuit realization of the ring DAC. There were improvements to the speed at which we were running the algorithms, and Andy McHarg, our technical director, he wrote a couple of new mapper algorithms that were released in conjunction with that. And then secondly, the output stage, we completely, Chris Hales, who's head of hardware design, he completely redesigned the output stage. This was actually a result of him being at home during the COVID lockdown. He had a lot of time at home on his hands, and he was investigating ways that we could again reduce noise, reduce distortion in the output stage of the DAC, and he came up with some breakthroughs there. We changed the active amplification components in the output architecture. in a way that just gave us lower impedance. We lowered the impedance compared to the pre-Apex model again, and reduced noise and distortion further. So those were the two main areas that were touched in Apex, but fundamentally it was evolutionary, not revolutionary.
Yeah, but it sounds like there was multiple elements that also evolved in this process with the Apex. It wasn't just a matter of like with a chip DAC, we would say this chip evolved, and this, it seems as though, as Imran was mentioning, it being a holistic approach, it seems like that was the entire holistic approach toward the DAC and how it fundamentally works was evolved in the Apex. So it seems like it may have been a pretty big jump. Can you speak on, Imran, can you kind of speak on the sound that we achieved with the Apex versus the non-Apex?
Yeah, absolutely. There's no question that great specifications typically also lend themselves to great performance, and we were certainly striving to achieve all the great things that engineers look for. Better crosstalk performance, better lower noise, increased linearity, and so forth. And we were certainly able to achieve that. I mean, one example of that is a 12 decibel increase in linearity in the third harmonic. That was huge. I mean, that's massive. And the way this presents, though, to our ears, which really matters, right, ultimately, is that you have a more crisp and focused soundstage as a whole. Instruments and music emanate from a more distinct blacker background. They're much more focused within that soundstage. The harmonic virtues of the music itself are much more true and distinct. It has, as folks will describe it, it sounds more real, it sounds more vivid, it sounds more natural. Dynamic resolution seemingly improved, but really what we're talking about is that anytime you can lower the noise, increase linearity, it provides seemingly to the ear and to the brain a perceived increase in dynamic response. But all of those are things that, I mean, if we're looking for better tonal accuracy, better imaging, better sound staging, a blacker background, these are all things that, of course, we as music lovers like to chase. And yeah, it was a tremendously successful iteration of the Ring DAC.
Yeah, okay. Just to add to that, I think one of the things that digital sources have been criticized for historically is sounding hard or glassy, or people have different words to describe it, but there's this sort of I think some people have called it digititis, a sort of characteristic sound associated with digital sources. And what I've noticed as through the generations of product which I've owned as a user, particularly as dCS has pursued odd order harmonic distortions, particularly third order harmonic distortion, they seem to be very closely correlated with that hard sound. And so I think one of the things that people found with the Apex upgrade, although the third harmonic was very low in level before, we were able to push that down another 6 decibels in the Apex upgrade. And immediately you get that feeling of sort of relaxation of, it sounds more natural, that there's just a little hard edge that disappears with the Apex upgrade. And I think it, from my perspective, it's directly correlated with that third harmonic distortion.
Awesome. Well, here at Reference Analog, we have, probably 5 dCS DACs in the store, from the Vivaldi down to the Lina. And we've noticed that between the different products, most or all the Apex DACs use technically the same board, right? They use the Apex board. The primary differences seem to be the power supply and the isolation and the analog board and how it's situated, and where things are sitting in the box and how they're isolated from one another. Can you speak on a little bit on the primary cause for the sound differences? Is it the difference in the cabinet construction? Is it difference in the power supplies? And how do these changes affect what we're hearing? And I think, Andrew, maybe you could start us off.
I'll start with that. Yeah. So you've characterized it completely correctly. The DAC and the DAC board contains the analog output stage, and that board is identical in all the Apex products. So exactly the same DAC, exactly the same analog output stage. So the differences lie elsewhere. And the two primary areas that differentiate the products as you move up and down the range are the power supplies and the cabinet construction, and particularly the isolation that cabinet construction affords. And so the way dCS typically develops a new product family is we start at the top. We start with a moonshot, what's the best we can achieve with the current technology and our current knowledge and what our suppliers can supply us. And we release a product that's the best that we can achieve at that point in time. And then we look at what can we remove from this bill of materials that will reduce the cost but reduce the sound quality as little as possible. So we want the best bang for the buck. Removes the greatest amount of cost but the least amount of sound quality. And we keep doing that until we've removed enough cost to reach a new price point, and then we cut a new product, and then we start the same process again. So we started with Vivaldi, we reduced cost until we got to Rossini, and then the same process again until we got to Bartok. And the two main areas where we found that we could reduce cost with the minimal impact on the sound quality was in the area of the power supplies. So, for instance, in the Rossini DAC, we have two separate power supplies. They're actually identical, but they're dedicated, one to the analog section and one to the digital section. The Bartok, those two sections share one power supply. In the Vivaldi, those two power supplies are actually tailored, one for the digital section, one for the analog section. So that was a simplification that enabled us to remove cost. Similarly, between Rossini and Bartok, we have a difference in the fundamental cabinet construction. The Rossini uses something called acoustic aluminium, which is almost like a sort of constrained layer, a sandwich with aluminium, rubber, and aluminium. So we have a base plate that's acoustic aluminium, and then we have a sub-chassis on which the circuit boards and the transformers are mounted, which is another layer of acoustic aluminium. And the transformers are mounted separately from the circuit board, which again isolates them from each other mechanically. In the Bartok, we've used aluminium plates, raw aluminium, and that sub-chassis is missing. And that enabled us to reduce the cost. So, back to Emran's point about trade-offs, where you have to make trade-offs to save money. We're looking for the trade-offs that give us the best bang for the buck, reduce the cost by the greatest degree, but reduce the sound quality by the least degree. And so, I think it's important to understand the thing that's constant between all these products is the ring DAC. They each have an identical implementation of the ring DAC. The DAC is the same, and the analog output is the same. The differences are elsewhere.
Then I'll just...
Yeah. Imran, is there anything you'd like to add for that?
So one thing that I was going to speak to is that with dCS, when we look at any given particular design, one thing that we do not compromise on is the quality of the componentry, right? Or and the specification to which we hold, those particular components to. So, for instance, the power supplies that we utilize in our products, they're the very, very, very best that we possibly can utilize. the components on our circuit boards, the standards of tolerance to which we hold, all of that maintains throughout. It's simply really a difference of how ambitious can we sustain with any particular design goal. So, for instance, even though you look at something like the Vivaldi or the Varese, right, the quality of execution is no different between that product and, say, a Lina or a Bartok. But obviously, the Varese and the Vivaldi are much more ambitious, but the quality and the standards to which we hold in that design process and in obviously the production process is no less stringent, no less stringent. We use the very, very best. It's simply that we can do more and can have more ambitious designs when we can, afford ourselves more chassis and, greater, a more evolved digital processing platform and so forth. But I think that's important, that the quality never deviates throughout our range. The quality never deviates throughout the range.